Good afternoon, good morning, people of Earth, and welcome to our SETI Institute Facebook Live. So today we are going to talk about asteroid, and for this I have the honor to have my fantastic colleague, Michael Busch, planetary astronomer at the SETI Institute and very serious scientist, I heard. So Michael is going to tell us a bit about 2006 QV89. So
Okay.
tell us why suddenly this asteroid is so interesting and important in our community.
Okay, so just first a note on the naming here. We've discovered a huge number of asteroids, about 20,000 we call near-Earth objects that come near Earth's orbit on the scale of the solar system. Hundreds of thousands more in the main asteroid belt, so we give them sort of telephone numbers rather than names. This 2006 QV89 is a particular asteroid that was discovered in 2006 by the Catalina Sky Survey in Arizona, which is one of the most prolific observatories in the world for discovering objects orbiting around the sun. At the time, it passed near the Earth, got bright enough to be seen. It was only visible for about 10 days before it went away from Earth and too faint to be seen. It has not been observed since until just this year because it was far away from the Earth. But even back in 2006, we knew we run the orbit forwards, it's going to come near the Earth again in September of 2019. And at the time, it was predicted that there was a 1 chance in about 7,000 that 2006 QV89 would impact the Earth on 2019, September 9th.
So what chance of a
Thus-
1/7,000, that means that, so in terms of probability, you're more likely to be eaten by a shark than to get this asteroid to kill you, right?
I don't know what the numbers are on shark attacks right now,
Okay.
actually, but what is this asteroid's almost certain to not hit the Earth, but we couldn't completely rule it out. Now we can. But the way we did this is kind of unusual, and that's what we're going to talk about today. I say we. I was not involved in any of these observations myself. We, in this case, is astronomers who are not me, so I should be careful
So
there.
there is a community of astronomers who basically are in charge of kind of monitoring those potentially hazardous asteroids. That's the way we call them,
Yes.
right? And this one was classified as a potentially hazardous because he has a number on what we call the Torino Scale.
So the Torino Scale is used for ranking larger asteroid impacts, things bigger than about 50 meters across. 2006 QV89 is actually smaller than that. It's between 20 and 50 meters wide.
So he will not have destroyed the entire
It is,
Earth.
even if it had actually been on an impact trajectory, which it isn't, we would not have any global consequences. It could have caused a regional problem. This motivated a group of astronomers working at the European Southern Observatory in Chile to do a rather unusual project. The idea was not to find the asteroid. At that time, it was too far away from the Earth. It was very faint. But you could work out, if the asteroid is coming on the trajectory that it is going to hit the Earth, it needs to be here in space. If it's over here, it's not going to impact. So the group down at ESO used the Very Large Telescope there, which is one of the largest optical telescopes in the world right now. And they looked at this one narrow patch of sky. I think that there should be a link in the feed to the story about this, which shows you the picture from ESO. There is no asteroid in that picture. There is just empty space and stars in the background.
So they used one of the largest telescopes in Chile, the VLT, to observe an empty patch of the sky.
To make sure that there was nothing there.
Okay.
So if the asteroid is not here, it's not coming straight towards us. It's going off to the side somewhere. We don't know exactly where it is off to the side. But the fact that there is nothing in this image says it is not going to hit the Earth in September.
So basically what you can see here, that's the observation of the empty area of the sky, and the red cross that are barely visible probably for you here are the location expected of the
If it was between those 2 points on the screen, then that would have been a potential impact. It's not there. Therefore, there is no potential impact. And this was back in July, the night of July 4th and July 5th of this year. So 2 months in advance, you can say this thing is not going to hit the Earth. But we still don't know where it is.
But in fact, people reported it later on, right?
So the asteroid is not going to impact, but it's still going to pass close to the Earth. It's now come quite a bit closer, and it actually can be bright enough to be seen with telescopes that can look over a wider section of the sky. There's this trade-off in astronomy. You're either going to look at a large section of the sky and you're not going to look for very faint things, or you're just going to stare at one section of the sky for as long as possible and find faint objects. Now that it's come close, they can survey the entire area of the sky where the asteroid might be, and it was in fact recovered last week between August 9th and the 11th. It was the week before last now. But now that it's become bright enough to be seen, observers in Hawaii and in Spain have in fact found 2006 QV89, and now we know exactly where it is. We can run the orbit out much further, and we can say that this particular asteroid cannot impact the Earth anytime in the next 200 or more years.
So they basically changed the classification of this asteroid, and now it's what we call a not hazardous asteroid.
We remove it from the risk list.
So everybody is happy. So it's not the end of... we're not going to be impacted by this asteroid.
Anytime in the foreseeable future.
In the next, 200 years?
Beyond 200 years, you could probably run the orbit out further, but it gets harder even with this now 13 years worth of data that we have.
So there is also, you mentioned that the orbit is not very, it's known for the next 200 years because of we have very few data points, right?
Right.
You basically have a cluster of points in 2006 and a cluster of points in 2019.
Right.
And we try to fit an orbit between.
We can link those two together.
And there is multiple solutions, of course.
So the problem, if I'm recalling correctly, this was not so much the multiple solutions. It's passing near the Earth, which is a great way to change the orbit.
Because Earth has a mass.
If it passes relatively near to us now, it will pass close to the Earth. It won't impact, but it'll pass close to the Earth again repeatedly, because its orbit is still on one that intersects with the Earth's orbit. That's why it comes close to the Earth at all. So you come closer to the Earth once, you come closer to the Earth again. That magnifies the uncertainties, and again and again and again, and eventually we can't predict exactly where it's going to be. And that's why after a few hundred years, we can't say if it's going to impact or not. So it's not going to impact any time in those next few hundred years.
So those perturbations which could change the orbit in one way or another in 200 years. But we talk about this one specifically. That's a very interesting target, but now we know it's not going to impact Earth for 200 years. But I read a lot of comments online, people saying, how come we didn't know where it was? How come we did not find this, we did not follow up this asteroid? What's limiting us here?
So in the case of 2006 QV89, again, it's very small. It's only 20 to 50 meters. It's smaller than the building that the SETI Institute offices are in, quite considerably smaller, in fact.
Oh, you're going to mention to our viewer we are in a small building. They think we are in a gigantic tower in the middle of San Francisco.
It's a pretty small thing. So even when it's a few million kilometers away, it's very hard to see. And that's why the VLT was needed, to make sure that it was not in that one patch of sky a month ago. Now, smaller telescopes can see it, but it's still pretty close to the Earth. In this particular case, it came close in 2006. It was seen then. And it was never close enough for anybody to see until just now.
So when you say it was not close enough to be seen, it's because an asteroid does not only reflect the light, right, coming from the sun. And when we observe invisible, we basically, if the asteroid is too close to us, we see it well. We have enough flux coming from the asteroid to see it. And when the asteroid is far away, and far away from the sun, on the top of that, is becoming fainter and is below the limit of detection that we have with our current instruments.
So the main effect here is just distance from the Earth, right? It's 1/100th as far away from the Earth as the sun. It's going to be 10,000 times brighter than if it's one astronomical unit. We call this 151 million kilometers, 93 million miles away from us. And that, even if it's at the same distance from the sun, it'll be too faint to be seen. And that's the case here. The object's orbital period is not 13 years. It moves through the inner solar system far more often than that. It spends most of its time here, but it's usually too far away from us to be seen.
So I just remind our viewers that if they have any questions about the topic of our conversation today, please feel free to post them on our Facebook page. We are going to take some questions later on. So the detection was done by the CFHT, the first detection. And at the time, the asteroid had a magnitude of 23 or something like this, which is...
It's about 23 and a half, if I remember right, but there's some uncertainty on that.
So that's very, very, very faint, basically.
So do a comparison for people who are not familiar with this. Under dark skies, the faintest thing most human eyes can see is maybe magnitude 7. Every 5 magnitudes, things get 100 times fainter. So we're maybe almost 15 magnitudes fainter here. That's almost 1,000,000 times fainter than stuff you can see with your eyes, which is why you need a really large telescope.
So at night, the asteroid, the brightest it can be, will be magnitude 21, which is still very faint and not detectable by most telescopes. You need to have typically a 1 meter, 2 meter class telescope to be able to see them.
Yes. Now the VLT is 4 8-meter telescopes all stitched together, if I'm remembering right. The exact specifications there. But that can see even a little bit fainter, which is why it was able to rule things out a month before everything else was.
So we finally found 2006 QV89, but we know that there is a lot of asteroids like this, right?
Yes.
This is really a flying rock. It's a 30-meter class telescope, 30 meter asteroid.
Yes.
So we don't know. We do know basically what its orbit.
Yes.
Its size, its shape. Do you have any more information?
We don't have much information on its shape. I'm holding here a 3D print of a different asteroid entirely, but we have more shape information on. It's not actually shaped, QV89 is not shaped like this. We don't know what it's shaped like, because all we have in our pictures is a dot. Now, if you look at the brightness of the object as a function of time, as it spins, you can say sometimes you're seeing less of the object, sometimes you're seeing more of the object. You get a sense of its overall elongation, how fast it's spinning. But that's really all we know about this one, is not too much detail.
So what kind of information we would like to know? If you had a perfect instrument, what information you will want to be able to extract about this asteroid?
He's asking me leading questions here. So most of my own research involves radar observations of asteroids. So if they pass near to the Earth, we can image them using radar facilities at Arecibo in Puerto Rico and in Southern California. And then we can get detailed images and make up 3D models like this. You can do some similar stuff with adaptive optics on large optical telescopes. Franck has worked on this. The near-Earth asteroids are too small even for adaptive optics imaging, for the most case. So we're lucky they come close enough for radar imaging. Unfortunately, QV89 turns out will be a bit too far away for us to observe next month.
So
oh well.
When you say it will not be observed by radar observation, using the Goldstone?
It is too far away for this.
For this one?
So we talked about how it's hard to observe optical telescopes and things that are far away from the Earth. For radar telescopes, it's even worse because the radar beam travels out and disperses as the square of distance, and then it disperses out as the square distance coming back. So we end up as 1 over distance to the 4th as to how well we can observe things. So something like QV89, we can only observe when it's very close to us, and in this case, we just wouldn't get much information.
So how many asteroids like this there is typically around the Earth? So
we talk about near-Earth asteroids. We typically mean things that come within about 50 million kilometers, 30-some million miles of the Earth, on their own Earth's orbit around the Sun, on their own orbit around the Sun. Most of the time, they're really far away from us, but there's a few 100,000 things that size, or 30 meters or so, or larger across. Things like this don't hit the Earth that often. Maybe once every couple of 100 years. The last time something like this did was in a place called Tunguska in Russia in 1908. But things this size do pass close by the Earth, close being a few 100,000 kilometers away, every couple of months. Again, space is big and the Earth is small.
So we have not cataloged all of them yet? We don't know the position of all those potential...
Down to this size, no. We could say nothing bigger than a kilometer wide can hit the Earth in the next few 100 years. We're tracking all of those objects. NASA has been tasked with tracking everything down to 100, 140 meters across in the near-Earth population. Below that, we just survey as much as we can, but we don't have anywhere near close to everything. Fortunately, those are less dangerous than the larger ones.
Okay, so we're going to take some questions. I've seen some questions already coming online. First of all, we have some hello from various places around the world, from Ottawa in Ontario, from Israel, from Chennai in India. Oh wow, a lot of, from Northern Alberta, from Scotland, from Green Bay, from Tampere, Finland, from Kurdistan, Kosovo, wow. From Portugal and New Zealand. And I think I mentioned everybody. I forgot UK and Florida. So hello, and thank you very much for following us. And please don't hesitate to send us in if you have any questions you have here. So I have some questions coming already. So one of them is that Is there any asteroid that might hit Earth in the next 20, 50 years? This is a question from Craig.
So the answer to that one depends on how big of an asteroid. Nothing larger than a kilometer will hit the Earth in the next few hundred years. We know that because we're tracking all of them. There's a very small chance that there's sort of a 100-meter scale one that we've missed. The survey programs will try to discover all of those, and the follow-up programs, including those I'm involved with, will track them and make sure that they're not going to hit. But we got into smaller and smaller sizes. Eventually, yes, something will hit the Earth.
Like Chelyabinsk.
So Chelyabinsk in Russia, I guess 6 years ago now, 6.5 years ago. Wow.
I know it was February 14. That's all I remember. I don't remember the date.
14th to 15th, yeah. In that case, an object about 20 meters across, so a bit smaller than QV89, flashed in the sky above the city of Chelyabinsk in the southern Ural Mountains in Russia. Nobody died, but there was about 1,600 injuries. We would like to know about most things like that before they happen. Tell people to stay away from windows. Current survey programs are designed to find most things like Chelyabinsk with a few days to a few weeks of warning, which is enough advance notice.
And the probability of this is typically...
Something like that happens somewhere in the world once every 30, 40 years. The next most recent one before Chelyabinsk was over the Southern Ocean, about, was it 800 kilometers south of Cape Town in 1963. We know about it thanks to satellites that were launched to ensure that nobody was setting off nuclear bombs without telling anybody about it. And they saw flashes over the middle of the ocean, but there was no high energy radiation, so it wasn't a bomb. Well, what was it? It was a large rock coming in and flashing in the sky. Something like that probably will happen somewhere in the world in the next 50 years. Mm-hmm. But we will not know about it probably too much in advance.
Except if we design this Sentinel spacecraft that observe continuously the sky and tell us when there is something coming towards us.
So people talk about building space-based asteroid survey programs. None of those have launched yet. And the ones that have been designed and seriously advanced are designed to looking for bigger things, 100 meters across and larger, because those are the ones that are particularly dangerous. And we're talking about deflecting. For something smaller like the Chelyabinsk impactor, survey programs are designed to provide short notice. So you can, again, tell everybody to stay away from windows, because most of the injuries from Chelyabinsk were broken glass. So even smaller things, a meter or two across, those hit the Earth's atmosphere and make interesting fireballs every year or two. Across the way here at the SETI Institute offices, we have Peter Uniskins, who is our professional meteor chaser. He runs towards explosions rather than running away from them. And he was in Botswana in the game preserve in the Kalahari there last year because an object a couple of meters wide, 2018 LA is the telephone number, was discovered by the survey programs, and then it quickly became clear this thing might hit the Earth tomorrow. So Yikwanzi down at Caltech in Pasadena worked with observers over in China and determined sort of the inverse of what happened with the QV89. He looked where 2018 LA would have to be if it had missed the Earth and determined it wasn't there. And thus it had flashed in the sky somewhere. And then reports came in from Botswana that they had had a big fireball at just the time that impact was predicted. Then Peter went over and with the staff from the University of Garumbe in Botswana, they walked back and forth through the game preserve for a few days, and they found little pieces of meteorite that had fallen out of the sky.
Fresh, pristine pieces of meteorites.
Just
asteroids.
Yes, it would have been a month after they fell out of the sky at that point.
Ah, a month after, okay.
So that sort of thing happens, again, on a yearly basis. It is mostly of interest to meteor hunters, because they want to go and pick up the meteorites, either for science or to sell to make money. But that is not a risk to anyone.
So we have a good transition for these next questions from Tom. Basically, the answer is going to be very fast, very quick. Do we know what 2006 QV89 is made of?
There are possibilities here. We don't have that much information. Again, we just have, I don't think anybody's got a detailed spectrum, so we just have the color. And it's not really that distinctive. It's probably a mixture of rock with some metal and some carbon compounds mixed in. Pretty typical asteroid material.
That's all. We don't know much about it because we don't know the albedo, in fact.
We don't have the detailed spectrum. We don't know the details of how it reflects light.
Yeah.
I'm hoping people get that information over the next month. We'll see.
So if we find out that an asteroid this size is going to impact Earth, is there any way to deflect this asteroid? This is a question coming from Trond.
So for something as small as QV89, you wouldn't typically talk about deflection. It's only a few tens of meters across. If that happens over a city of 1 million people, like happened in Chelyabinsk, then you have to do a whole bunch of stuff to prepare. You want to get everybody away from windows. You may talk about evacuating sections of landscape. If it happens over the middle of the ocean, as happened in 1963, it doesn't really matter that much. It just flashes in the sky. There's maybe a few interesting small waves, and that's it. Something this small can't cause that much damage at the ground. Although Chelyabinsk, again, not that much is not zero. There was a lot of injuries there, but nobody died in Chelyabinsk. Something larger, 100 meters or so across, that could cause a far more serious problem.
So that's a question from Frances, in fact. So you're answering to your questions already, so go ahead.
So
what happened with 100
for 100 meters across and bigger, that's the point where no matter where it's going to impact on the Earth, it's worth talking about making it not be on that trajectory anymore. For that situation, you need to have a lot of advance notice because it takes time to build and launch a spacecraft. So this 140 meter lower limit where NASA is ordered to find everything larger than that size is pragmatically set. It's that lower size where finding them and deflecting them is worth doing. So there are multiple ways to do this. People back in the 1980s, 1990s talked about deflecting asteroids with nuclear bombs. This is almost certainly not necessary. And it's probably severe overkill because we've ruled out the really large asteroids. Nothing a kilometer across is going to hit the Earth anytime soon. For smaller asteroids, there's two main approaches that people focus on now. There is something called gravity tractor asteroid deflection, which is very slow, but it's very gentle and well controlled. You have a spacecraft here, you have the asteroid here. There is gravity between them, very weak, but it's there. So if you angle your rocket exhaust so that it misses the asteroid, you can pull the entire thing off course very, very slowly, because the asteroid's gravity is pulling your spacecraft this way, equal and opposite reaction. Newton's third law, the asteroid is getting pulled that way. Sounds kind of Star Trek. You're pulling the asteroid towards you by standing next to it, but
there is no gravity.
You're all in free fall here, so you go very, very slowly. You can pull an asteroid thousands of kilometers off course over several years. This requires some pretty durable spacecraft and some pretty careful flying, but it can be done in principle. NASA proposed a mission to do this, among other things, called the Asteroid Redirect mission. The total mission cost was $2 billion, and NASA was not given the money, at least not yet. There's another technique for deflecting asteroids, which is a little bit easier, but not as well controlled. This is kinetic impactor deflection. You just hit the asteroid with a hammer, and you shove it out of the way. A hammer, in this case, is as big a spacecraft as you can launch, going as fast as possible. And pure momentum transfer, you shove the asteroid off course. This is faster. You apply a velocity change, maybe it's a few centimeters per second, but you can do that a year in advance, then you've moved the asteroid however many thousands of kilometers, and there's not a problem. But it's not very well controlled. This is a pile of rocks. How does it react to you running into it? We don't really know the answer to that question.
So we have a mission to do this.
So NASA and the European Space Agency have a project called AIDA, and part of that project is a mission called DART, Double Asteroid Redirection Test. The idea here is to launch a spacecraft, which is to launch in 2021, so just a little under 2 years now. And they will go out to an asteroid called Didymos, which is a binary asteroid, actually. There's a small satellite orbiting around a larger asteroid. And they will run the spacecraft at 6.5 kilometers per second, which is some point something miles per second, into the satellite, Didymos Beta. The spacecraft will be destroyed on impact. It won't be completely vaporized, but that which isn't vaporized will be rendered into very tiny pieces. But all of its momentum will go into the secondary, Didymos Beta. And that will change the orbit of the moon around the main asteroid. And measuring that the change in the orbital period will tell us how much momentum got transferred and how the asteroid reacted to that impact.
So that will be a way to calibrate basically, to understand truly the effect of kinetic impact.
And demonstrate there is at least one technique we have, in fact, moved asteroids around.
So that would be a big deal if it works.
One note here. The DART mission has very carefully designed it so that they are shoving Didymos Beta and Didymos Alpha, which it orbits, further away from the Earth. Didymos cannot hit the Earth anytime in the foreseeable future, and they are pushing it even further away. This was a key point in the environmental impact statement. You won't don't create the impact hazard.
We made sure that we are
demonstrating the impact hazard.
Yes, so
don't make rocks fall from the sky.
Yeah, so that's good transition to the people who think that we're not controlling what we are doing, but we are. Is in case there is a potentially hazardous asteroid that is going to impact Earth, will we ever be told? That's the question from Anthony.
So astronomers are really, really bad at keeping secrets. This is actually by design, because we want follow-up observations, particularly for asteroids. We want follow-up observations so we don't lose them. So the initial discovery notifications for 2006 QV89, 13 years ago, and every other asteroid that's been discovered for the last couple of decades get announced via the internet, email. You can get alerts sent to your phone now, if you want to, within a couple of hours. And
minutes even.
They're going to try to cut that down to about a minute with the Large Synaptic Survey Telescope project that's getting built in Chile, because we don't want to lose anything. And you find an object with a telescope, you can't observe it that long, particularly for optical telescopes, because eventually the sun comes up. And you want people a few time zones further to the west to use their telescopes to look at it. So it immediately gets blasted to a global network of astronomers, and it's all public information because we want everybody who can possibly do follow-up to do so. Also, you can't really hide an asteroid, because if you can see it, somebody else with a similar telescope can see it. It's right there on the sky. Mm-hmm. So it would be kind of pointless to try to hide a discovery.
And I will simply say that we report observation of asteroids in multiple databases. One of them is the Minor Planet Center.
Yes.
So for those who are really interested and want to see, so in the Minor Planet Centers, you have the coordinates and the orbit of the asteroid, and you have all the observation reported for the asteroid. So you can also do that yourself if you have some knowledge on mechanical, celestial mechanics, to be able to do this analysis yourself. So that means that the data we use are publicly available. So anybody can basically find. And
all of the impact forecasts that we've been quoting, which is run the orbit forward, we have some uncertainty in where it is, how fast it's moving, we run that forwards with time. All the math and methods used for that is public, and it's run in parallel by the Solar System Dynamics group down at the Jet Propulsion Laboratory in Pasadena for NASA, and then by a group in Europe. It's been run at the University of Pisa, but I believe they are now moving to another location just outside of Rome for the European Space Agency. And there are other groups that do similar forecasts, all in real time, all constantly checking each other's math. Not so you're near real time. It takes a few hours to update the models.
Okay, so now I have a very difficult question for you. What does an asteroid smell like?
So
I'm enjoying this moment.
This is an interesting question. It depends on the asteroid. So I have not actually smelled any asteroids that are out in space.
Well, you've been working on asteroids for how many years now? 10, 15 years, and you never get the idea of smelling an asteroid?
The asteroids are up in space. I'm down here on the ground. I have smelled meteorites.
Very disappointed, Michael. Very disappointed.
I have smelled meteorites. Nickel-iron meteorites. There's a couple % of asteroids that are made of metal. Nickel, iron, a few other things mixed together. Here's a sample. Those don't really smell like much of anything. If they've been sitting on the ground, the metal rusts because water and oxygen, and then they smell like rust. But then you're not really smelling the stuff that was up in space.
Maybe we should ask Peter. Peter has been collected some fresh ones.
There are asteroids called carbonaceous chondrites. They have lots of carbon compounds in them, 4.5 billion-year-old stuff. That kind of smells like tar. If you heat it up, then more stuff becomes volatile and goes into vapor, and then you can smell that. I don't recommend it, though, because if you heat carbonaceous chondrites up to a couple hundred Celsius, maybe 400, 500 Fahrenheit, so the top end of a kitchen oven, then you get fun things like mercury and arsenic. I think there's some cyanide. I don't want to smell that myself.
You don't have the curiosity to do it yourself?
Not personally, no.
Okay.
This actually is a problem. People have talked about space resource utilization. There have been many groups, commercial and publicly funded, that have investigated this. If you go to asteroid material and you try to start processing it, say you want to get water for astronauts to drink, how do you make sure that you don't have cyanide, arsenic, mercury in the water supply?
All right.
Try to avoid that.
So this is the last question for me. So what you're working on now? What is exciting you at the moment in your research? Tell us something unrelated maybe to asteroids, something else.
So I have actually a little frustrating situation which has been occupying my attention the past week. Last month there were a few asteroids that flew close to the Earth. We had a brief story on the SETI website about that. One of them, 2019 OD, I observed back in July. Except when I looked at the data from the telescopes I was using, which are elements of the Very Long Baseline Array, which is a set of telescopes spread across what's currently the United States, we found there's no sign of the asteroid in the data. And it looks like all the telescopes were pointed very slightly to one side of where they should have been.
So you're basically telling me that all the telescopes did not point to.
No, it's possible that they actually were pointed where they were, and the file that says this is where the telescope was pointed is wrong.
Okay.
But I've been spending the last couple of weeks digging into the documentation and the engineering here. Is like, why don't I see an echo?
All right. So the reason I ask you this is because I like when people tell us the non-glamour part of science, and this is totally a non-glamorous part of science. When you spend a lot of time trying to solve a very stupid question, which is why telescopes were not pointing to the right
I have made this
position.
mistake before. At one point, I forgot the fact that the Earth's spin axis is not actually stable, and it precesses around. And I used positions that were accurate for 1950 as opposed to now, which turns out to not work anymore.
Okay.
That was embarrassing.
I do remember. I'd made the same mistake, so don't worry.
Fortunately, the telescope operator caught that one, so those observations worked. But I'm still trying to figure out what mistake we made last month.
All right. Well, thank you very much, Michael, for joining us and telling us you love about asteroid. And I hope that in the future we're going to have the opportunity together to smell what an asteroid is truly made of.
I might leave that to you, depending on which
what
object
that
is
will be.
involved.
I'm very disappointed. Okay, so thank you very much to all our viewers, wherever you are on this planet. Don't forget to follow us on our social media, Facebook, Twitter, Periscope, YouTube, Twitch, everything. We're everywhere. So, and of course, join our website, register to get our newsletter to know everything about what's going on in the world of space exploration, and asteroid. Thank you very much, Michael.
All right.